Hi everyone, welcome to the first video on Dart Academy. This is gonna be on how to train a Llama 2 model. We're gonna be using this script that you're seeing on the screen. I'm gonna share with you this script. We're gonna cover the different topics on this, how it works, how it's gonna go. And mainly for this first video, I will have a brief explanation on how this whole process works, what we're doing in here, like why this is relevant or important for you, the end user. And basically, to start with, let's cover this first part of the script, which is basically at the end. So to start with, what we're gonna do is we're gonna fine-tune nose arms Llama 2, 7 billion parameters. This is gonna be the model we're gonna be training. The reason I usually use nose arms is basically because it is much less restricted than the Llama 2, the vanilla Llama 2 from Meta. And basically, this is gonna let us do more things that we wouldn't do without prompt engineering quite a lot on Llama 2. So basically, I usually go for nose arms to try it, see what I can do with it, and if it doesn't fulfill my needs, I'm just gonna look for another model or fine-tune this model on a 13 dataset. So what we're doing here is basically we chose the Databricks Dolly 15K in order to train the model. Basically, this is a short and very good model dataset to train on, because this is gonna be good for your GPU, because it is not quite huge, it is quite complete, so it's gonna work very well just to fine tune the model. I don't know if nose arms is pre-trained on Databricks Dolly 15K by default or not. It's not on top of my mind, but basically we're gonna see how it goes. This is just for you to learn how to do it. You can choose whatever data set that you need, whatever model that you need. If it fits on your GPU, it's fine for you. You're ready to go. So basically, we chose this data set. We're gonna see what this load data set function does. We're gonna print some parameters from this. We're gonna choose, also we need to provide a VMV. So VMV is bits and bytes configuration for this. We're gonna create it. So basically this bits and bytes thing, if you don't know about it, is basically we're gonna be compressing the model so that we can train it on a smaller GPU, like more consumer-based GPU. I'm training everything on a 3090, and you're likely gonna need a 3090 if you want to train a model like Llama 7V. If you want to go under 7V, it's very likely that you can train this thing on a smaller GPU, but I've been unable, and I've tried quite hard in order to train these kind of models on smaller GPUs, but I've been unable to do it. So recommended, go for 3090, go for good hardware as well, like i7 if you have it on your machine, and something like 32 to 64 gigabytes of RAM, of computer RAM, minimal, because otherwise it's going to be quite hard to make this thing quite fast. So basically, we're going to create a config. We're going to see how it looks like. We're going to load the model. We're going to also check which is the biggest length that this model can fit for your prompt plus generated content. And finally, we're gonna pre-process this data set right here. We're gonna save the checkpoint of the model, because basically what we're doing in here is low rank training. We're not fine-tuning the whole model. We're just gonna be fine-tuning 13 weights on the model. So basically, instead of fine-tuning all 7 billion parameters, we're gonna be training much less. I think it's gonna be something like 1 million, around 1 million. So the first papers that refer to this technique were the famous Stanford adapters, like alpaca models. They were basically these low rank additions that you do on the fine-tuned model. So basically we're gonna train and save the low rank parameters on one file. We're gonna also save it on a merged file, so that you just can load the merged model and you just can forget about the LoRa. You can, in theory, load the LoRa or the adapter on a different model. It is something very common for the case of, has called the diffusion model. So basically, what you do is you load Stable Diffusion, then you load different LoRa's, and basically different LoRa's will load different tasks depending on which is the task that the LoRa is trained on. So this is quite common on diffusers, and it's getting quite common as well on LLMs. Nowadays, it's kind of the way to go if you want to train models for this kind of use case. So basically, we're gonna load this thing in here. We're gonna load the model from the file, and basically this is gonna be the place where we're gonna be saving the merge checkpoint of it. Okay, the whole model. So it is also important to save the tokenizer, because if you use a different tokenizer with a different model, so basically the tokenizer should always go hand in hand with the model, because otherwise the tokenizer is going to generate a vector of integers that is nothing similar to what the model can understand, and it's going to generate just garbage. So in order to avoid these kind of problems, I usually recommend just save the tokenizer. It's a small file. I know you can find it on the internet. If you're, for example, using Nose Arms, we're not training the tokenizer, you could just get into Hugging Face and download the whole thing. But in my opinion, it's better to just go and save it right after you just save the trained model. So yeah, we're using Hugging Face again, just in case you missed that, because it's quite easy and convenient to train things on Hugging Face. These are the different libraries we're gonna be loading on this script, and basically let's cover some of these functions on what they actually do. Basically, we're getting the number of GPUs that we have, we're sharing a max memory. This would go something like 24K, but I'm just leaving this way because it just works on these kind of models. Also, it's quite important to provide the VMV config that we are going to generate on a different function. So the bits and bytes configuration, it's basically telling the model how to compress the different weights, and it's quite necessary. If you have a big enough GPU, you could just forget about quantization of models, but I don't think it's my case. And I don't think it's the case of many people, to be honest. So that's what we need to do. The GPU pours, we just need to do this kind of thing. Then we're gonna get the tokenizer as well. So load model is gonna load the model, load the tokenizer, and we need to do something more, and this is quite important. So basically, when you train a model, a LLaMA model, or any other LLM that's basically doing this causal inference on tokens, what we need to do is we need to make sure that every single instance on the data set has the same length. Basically, how you achieve that for those prompts that are shorter on your data set, basically you pad on the right usually, even though it's possible also to pad on the left. I think it's less common. You usually go for pad on the right, and you fill it with pad tokens, and we need to tell it what pad token is in this case, because as far as I know, it is not something given on the model. So basically we're going to be using the end of sequence token for this. Okay, so basically we return both. Then it's important, if we are training a model on a dataset like Databricks Dolly 15K and it follows a 13 format, we better follow the same format. We could just ignore that and just keep going, but it's gonna have a worse performance, truly. So the best way to go is basically try to adapt your dataset or your data things that you have or whatever into this kind of format where you have an instruction, an input, a response, a context, depending on how the foundational model has been trained on the prior. So basically we just provide this kind of thing in here. Then we get which is the maximum length that we could have for the model. So this is basically 44,096 4K for the LLaMA2 models. Then we preprocess the batch, preprocess the data set. How we do it is basically we just fill in the batch text column, and basically we just tokenize it and return the list of integers. That's what we do. Basically, we just create a data set. This data set is going to be given to the model during the training. Basically, this is what this function is going to do. Yeah. So let's move on. This is quite relevant. This is possibly the most important thing that you should pay attention to, which is bits and bytes, as I said before. If you don't configure it properly, it's gonna affect the performance. Like, you should configure it properly, like in order to make sure that your model is gonna be trained with good enough capabilities. So we're gonna be loading the model in 4 bits. This is the, like, if your GPU can handle big models on training, you should just forget about the bits and bytes, because as you are compressing the model, you're basically doing quantization, your model is going to perform worse. So it's if you have enough VRAM for this, just go that way. But usually for everyone that's using consumer GPUs, we just go for this kind of thing. This is what I usually use for all the models I train. This goes quite fair, quite good, and I think this is basically taken from the Hugging Face documentation, so not too much thought given. But you could try different quant types, different compute types. They are restricted as well, so not all the different PyTorch types are gonna be possible to be used in this way. So bits and bytes is a way to do quantization. You have other methods like GPTQ, or you have other methods like I think it's called AWQ. You also have the quantization done by LLaMA2, right? So yeah, we're gonna leave it this way. So another important thing is, basically, as I mentioned before, we're gonna be doing low rank training in this kind of thing. We are also using the PEF, the performance efficient fine tuning from Hugging Face. That library is gonna be used as well. So this is the configuration that we're gonna give it. We usually use this thing in Dart, and this is going quite well as well. So yep, we just basically go for this one, and we apply this thing to the different feed forwards inside the transformer. So the Llama transformer is going to have different feed forwards or dense layers or linear layers. It's called linear layers in PyTorch, but basically if you are a TensorFlow fan, you're going to say them called dense layers. Basically what we're doing in here is we're going to be applying the LoRa on those layers. We're not going to be modifying anything related with we're not going to be modifying anything related with the different matrix, like the Q matrix, K matrix, P matrix on the transformer. This is the training process. We're going to be doing gradient checkpointing, which is going to reduce the usage of VRAM. We're also going to be giving these parameters. Okay, we're going to be generating the PIF config. This is basically going to give us the model. Okay, we created the trainer. We provided different steps, different things we're going to be going for. We're going to be training in this case for 1 epoch, just to make it quick, but you could train for longer epochs. Usually, large language models are trained on a reduced amount of epochs because they are zero and few shot models, so they're capable of learning on a very reduced number of epochs. So there's not much to be checking here. Basically, we just go for the training. We're just going to provide some metrics on how the process goes. Basically, we're going to save the last checkpoint of the model. So as I mentioned before, we're going to save separately both the LoRa and the merge model. And in theory, you could put the LoRa on a different model, on a different pre-trained model. The only problem that I could see is if that LoRa sizes are not compatible with the model, but otherwise it's gonna go fine. All right, we just have more helper function in here, and basically the rest of the code is gonna be for the training process, as we mentioned before. So we have opening here. This is basically this command that I'm just gonna give you guys. basically is NVIDIA SMI minus L to make it loop. All right, it's gonna be training continuously the different parameters on the GPU, like the usage of the RAM, the usage of the compute, which are the different processes running things on the GPU, which is the GPU usage, all the different parameters, right? So we are gonna also go for the training right here, okay? And we're gonna see how the usage of the GPU is increasing. So basically we have 15K prompts. Okay, we have, it's gonna load the thing. We're also loading from cache data, because I've been running this before. I've already recorded this Spanish version of this video, so it's right there. But yeah, it's 5 gigabytes of usage right now on the GPU, and it's gonna keep going up until we reach 19 gigabytes, around 19 gigabytes. So we may have 5 gigabytes free for this 3090. So basically, we're gonna be seeing right here. We're gonna be seeing right here the different results from the training. This is basically epoch 0, and it's gonna stay in 0 because we're gonna training for just one epoch. And basically, we're gonna be seeing the loss going down. This is the gradient descent phase on learning which are the different combinations given. Yep, this is pretty much it. Something relevant in here is the learning rate. So what's gonna happen is we're gonna start with high learning rate, and we're gonna start reducing the learning rate up until the end of the epoch. So it is possibly one of the hardest parameters to set when training an LLM. We can use different parameters or usual parameters values for this learning rate. We can use a dynamic learning rate, as we're saying in here. It's being modified a certain amount every single epoch, or we can just use the same learning rate. It's recommended to use a dynamic one, something that you start with a learning rate quite high for the values of learning rate, and then you start reducing the value up until you reach the end of the epochs. The reason to do that is you want the model to learn to try to do gradient descent quite aggressively right at the beginning, and then basically when you are just finishing the epochs and the training, you just basically reduce the value so that it tries to stay close to the values that it's going around, right, without just going on quite different directions otherwise. So basically we just train the whole thing. Okay, this is the ending loss right here, so basically 1.43, and these are the different parameters for the training phase. Yep. So basically it is setting the last checkpoint of the model. We're gonna see what happens when we try to run inference with this model. We're gonna see the output of it, so let's see where it outputs, but don't expect it to be quite great. Like the demo before for the Spanish video wasn't that good, and we're just gonna keep on the same, and we're gonna see why that happens. What is the problem with the prompt? So let's run it. Something interesting. Well, I'm running on CUDA. This is the inference script. You're gonna have all the code right on the comments. It's part of the Dart.ml repository, so you can go there, download this code. So it's gonna be on the description of this video, just in case. Basically, you can uncomment these different parameters if you want to do a more efficient loading for your hardware, or obviously you're gonna receive less capabilities from it. But in this case, it's fine because this is a quantized model, the one that we have trained, so there's no problem in there. In fact, we're kind of doing QLoRa in here, okay? So this is basically the model. We're gonna send it to the CUDA. These are the inputs. We're gonna send them to the CUDA. This is the prompt. We're gonna tell it how to play chess. We're gonna see what happens, and we're gonna try to explain why that happens. Finally, we're gonna load the tokenizer, we're gonna load the model, and we're gonna give different parameters on the generate kind of function. So what's going on here is we're gonna configure temperature to look for creative, or look for the outputs to be more creative. So each time we run it, it's going to very likely give us a different answer. It's going to be undeterministic. If we just give temperature 0, it's always going to give us the same answers back. And we're also just asking for 100 tokens. We could ask for more, but this is just for testing. We're also just considering this top P parameter in here. These are the input IDs, which are basically the tokenized values of how to play chess. And this is the output that's going to be printed. So just in case, let's try to run it. I just changed a couple of things, so haven't tested since the last video. Let's see what happens. And as you can see, this is let's see the usage that we have on the GPU during training, like the highest, so that you guys can see. It's around 19 gigabytes of RAM. Yeah, just give me 1 second. Yeah, right here, as you can see. So the usage by the Python code is gonna be like 18 gigabytes. Like if we increase even the amount of the usage for the monitor and all that kind of stuff, that's gonna be quite higher. So we're loading the checkpoints, we're loading the model in here, we're also doing GPU in this video, I guess. So let's see what happens. Let's see what is the output. Don't expect it to be too good. I'm gonna try to explain what happens. Yeah, so just let me do a couple of things. So I changed this thing before because I was running on the CPU. I need to double check what happens when you try to do it on the GPU. So let's run it. It's gonna take a bit. Let me try to explain what's gonna happen. So it's gonna be incapable of understanding what we're asking it. Like we're asking how to play chess, but the model hasn't been trained on how to play chess directly. Like the way we have trained this model is by basically telling it a format, and we need to follow that format if we want it to work. Like we have told it, hey, this is instruction, this is the input that I give you, this is the response that you should produce. And we are not giving this kind of a structure, we're just asking it how to play chess. So it's going to be confused, and it's going to start generating text that doesn't have to do with this kind of thing. Like it's not going to be able to answer that. So this is kind of the prompt engineering part. This is the prompt template, if you want to call it this way. And this is something that you can easily do with frameworks like GPT-4o. Like you can provide a template, and basically you would just write down as you would do with ChatGPT or any other model, and you would have it ready to go. But yeah, this is basically for testing, and we don't have it just right there. Let me show you what is the output that we have. Well, there's no output because basically just clear everything. Just in case we could see before. This is the time it's taking, by the way, to do the inference using the CPU. We're not using GPU in here. I need to check something on the script. As you can see, there's nothing loading on the GPU. We just have the monitor usage for GPU. So yeah. On a 3090, you are also likely to be able to train a 13 billion parameters model without any problems. So you could do it as well. Also, if you're training 7 billion parameters, you're gonna be fine to go on a Google Colab. So I'm gonna make another video so you guys could see how to train these models on Google Colab. For free. Yeah, I mean Google Colab for free without needing the enterprise version or providing any tokens or anything. Just the instance that you receive for free from Google. Yep. So this is basically, let me just try to check all the things while we wait for it. Yeah, so as I mentioned on the Spanish version of this video, I usually like to go for no terms instead of going for the vanilla version of the LLaMA2 model, because it is quite censored. The LLaMA2 models are quite censored, and basically we are able to do a lot of technical things with it. I usually use LLMs to do other tasks like programming or just try to play around for certain use cases like NLP, but it's pretty hard to do it with the vanilla Llama 2 version. So I usually go for Nose Arms Llama 2, to be honest. Yeah, and Databricks Dolly 15K is a quite small data set for the size, but it's quite good. So I usually test it every time I try to fine tune a model. I try to test it to see how much time it takes. Like, I mean, if I'm testing if my GPU supports 7 billion parameters, I could just use that. The same happens for 13 billion and 34 billion. Nowadays, like, the most I've been able to train on a 3090 is 13 billion parameters. Nothing beyond that. So yeah, you may need to just add another GPU if you want to train beyond that amount. Okay, so basically this is the generated output. Below you can find the complete text of this game, and it just outputs some chess movements. Well, this is basically what happened. If you are curious of what happened on the video explaining how to do this thing in Spanish, it wasn't able to do this even. I just output a bunch of instruction and results from a different question, so it wasn't unable. So yeah, basically this is the end of the video. I hope you liked it. Subscribe, hit on the bell to receive notifications with new videos coming up. Any question, any suggestion, anything that you would like to mention, like any mistakes I may have made during the video, just let me know. Any suggestions, anything that you would like to see on future videos, courses, whatever, let me know, and see you in the next one. Bye bye.